Hello everyone, welcome to the NPTEL course 22nd lecture of NPTEL course on scalable data mining or scalable data science, and I am Professor Shourangshu Bhattacharya from IIT Kharagpur, and today's lecture is going to be on alternating direction method of multipliers. So, today we are first going to discuss the distributed gradient descent or rather we are going to recall the distributed gradient descent and distributed optimization problem, and importantly we are going to discuss distributed optimization as an equality constraint problem, and then followed by that we are going to discuss the precursors to ADMM, which are some of the methods that we will discuss for solving the equality constraint optimization problems, and we will discuss their limitations. So, what are the limitations of these methods, and then finally we will discuss ADMM, and which basically overcomes some of these limitations, and then we will also discuss an example, a toy example of how to use ADMM for a practical machine learning distributed optimization problem. Okay, so distributed optimization. So, in the context of machine learning, the distributed loss minimization problem can be written like this. So, basically we have we have the data point x. So, our data point is x, okay, or rather xi. So, xi has all the data or rather sorry the data point is ui and vi. So, our data point is ui and vi, and the parameters with respect to which we are going to optimize are x. Okay. So, basically our Li of x is the loss function, which is a function of basically x given ui and vi. Okay. So, our loss can be decomposed like this, where I rather break down the data into clusters Cj. Okay. So, jth cluster or jth group, we can say jth group, and for all the examples I in the jth group, this inner term, it sums up the loss for those data points, and then there are m groups. So, there are m groups. So, the outer sum basically sums up over the groups. Now, the thing is that maybe each of these groups or clusters are distributed onto different machines. Okay. So, then our total loss function looks something like this. So, the first part is the loss, which is dependent on the data, and it can be broken down in a hierarchical manner into the loss over the data points in a group, and then also the total sum over of the loss over all groups, and then we add the regularizer, which is not dependent on any data point. Okay. So, this is a typical structure of an optimization problem that we get in machine learning. Now, given this structure, what will the gradient descent algorithm look like? Okay. So, the gradient descent algorithm will look like this, where just like your loss is hierarchically broken down into data points within a group, and also the sum over all data points within the group, the gradient can also be similarly broken down. Okay. So, you can calculate the gradient over a group. Okay. This can further be actually pushed inside Okay, but for the time being you can just say you want to calculate the gradient of the loss of data points in a group and then sum them over, and then you can get the total gradient. Okay. So, the advantage of this strategy is that you can compute this inner gradient by just independently on each computer, okay, and then you can communicate it to a central computer. Okay. So, then you can compute the total loss on gradient on the central computer by adding over the individual gradients of the jth groups, okay, and then you can do this update where your alpha can, in case of gradient descent, be chosen by line search, or if you are using something like minibest stochastic gradient descent, you can use a alpha which is you can use alpha is equal to something like 1 by root k. So, alpha can vary with the number of iterations. Okay. So, the problem with this is basically that this is kind of slow for most practical problems. Okay. Okay. So, and basically the reason it is slow is that you are not doing much computation on the nodes. So, what you are doing is you are just calculating the gradients on the nodes, and then you are transferring the gradient for each iteration onto the central computer. So, you are doing a lot of transferring of data onto the central computer and doing relatively less amount of computation in the central node. Okay. So, sometimes it is also called that it is communication wise it is not very efficient. Okay. So, we want to solve this problem. Okay. So, the general strategy for solving this problem will be that we want to do some optimization also on the nodes, that is a few iterations maybe on each of the nodes, and then somehow exchange parameters with the central computer, so that I have to exchange the parameters with the central computer a less number of times. So, that is the general idea behind ADMM. Okay. So, but before going into ADMM, we look at some precursors of ADMM. Okay. So, why do we have to go into this precursors of ADMM? The reason is that you can understand. So, before looking at this precursor of ADMM, you can understand that if you have decomposable function, which is as we had written down, which is sum over j is equal to 1 to m, let us say, and then Lj of x. Okay. Suppose this is our this is the function, plus there is some regularizer which I am not so much bothered about at this point in time. Okay. If this is the function, okay, so we want to minimize this Lj of x on the jth computer, but then the x, let us say there are two computers, let us say j and j dashed. Okay. So, then the x variable on the jth computer and the x variable on the j dashed computer are coupled together. Okay. So, how do you express this coupling? You can express this coupling by slightly modifying this optimization problem in this manner, that you, instead of writing x here, you write xj, but then you add the condition, or you add the constraint rather, subject to the constraint that xj equal to x j dashed, something like this. Okay. So, some equality constraint. Okay. So, this constraint rather sorry. Okay. So, this equality constraint is what we want to tackle. So, this is going to be our idea. We will see how exactly we do it as we go forward. So, basically what this brings us to is this equality constraint problem. Okay. So, the equality constraint problem basically looks like this, that you have to minimize f of x subject to the constraint that a of x equal to b. Okay. And now from optimization theory, as you can write the Lagrangian. So, this is the Lagrangian for this particular problem, and this is the dual function. Okay. So, the dual function is basically the infimum. So, the dual function is the Lagrangian function is of course a function of the primal variable and the Lagrange multipliers, which is y, and now the dual function is only a function of the Lagrange multipliers, and it is the infimum over x, a Lagrangian of x comma y. Okay. And then you can also solve the dual problem, which is maximization problem if the primal problem is minimization problem. Okay. And the final solution is of course you can show that you can either solve it, you can solve it basically in a minimax manner. So, you can compute the, you can take the max over y, L of x comma y, and you can compute the min over x, or you can do the other way round, and in case of convex optimization problem the two are the same. Okay. So, the dual ascent method tries to solve this problem in this manner. Okay. So, it tries to do a gradient descent, or it tries to do a gradient descent step for the dual problem. So, if you recall, the dual problem is that you have to find y, which is arg max over y, and then L of x comma y, or rather sorry, this is rather, if I were to write it like this, it is arg max over y and then infimum over or minimum over x, L of x comma y. Okay. So, this is the dual problem, and so basically you have to compute this function minimum over x L of x comma y. Okay. Another way of saying it is that you compute the x tilde, which is the minimum over x L of x comma y k, and then you once you have computed the x tilde, you substitute the x tilde in the gradient, in this gradient, and then you compute the next iterate. Okay. So, this results in this algorithm. So, at each step, so first you randomly initialize some y, okay, and then you compute the next iterate of x by solving this problem, the inner problem, and then once you have solved this inner problem, you do a gradient descent step. So, this is the gradient descent step here, okay, for the dual variable. Okay. Now, the problem with this method is that it works only if this Lagrangian is strictly convex. Okay. In other words, this solution x k plus 1 for this problem should have a unique solution. Okay. So, otherwise what happens is this step can have multiple solutions. Okay. And even though the Lagrangian value will decrease, because this step is having a multiple solution, and you have no control over which solution gets chosen, the update to the dual variable will oscillate. Okay. So, this is the problem with the dual ascent method. Okay. And also another problem is that this should be bounded below. So, it cannot be unbounded. Okay. So, a generalization of this dual ascent method is called the dual decomposition method, where the method is exactly the same, except that instead of f of x as one function, you can now have f of x as sum of many functions. Okay. So, your objective function f of x is now separate, it is called separable. Okay. So, your objective function is separable. Now, if this is the case, if your objective function is separable, then what you can do is, you can, as mentioned earlier, you can write so you can write the problem of minimizing. So, you can write the problem of minimizing over x, f of x, as that of minimizing. So, these two problems become equivalent. You minimize over x 1 till x n. So, you take n variables and then you write this whole f of x again, which is a sum over f 1 x 1, f 2 x 2 till f n x n, subject to the constraint that x 1, and also of course x is a variable, and subject to the constraint that x I is equal to x. Okay. So, if you have a constraint like this, then you can write the Lagrangian function as this. Okay. So, this can be written as a of x I is equal to b. So, this is in this form, that a of x I is equal to b. Okay. So, your L is now separable in x. Your Lagrangian function, as you can see, is separable in x. So, x are the primal variables and y is the dual variable. Okay. So, if that is the case, then your earlier x minimization step, it now splits into this capital N many minimization problems. Okay. So, your algorithm now changes slightly. So, it is same as dual ascent, except that the first x minimization step, it is now split into n optimization steps. So, see that here what we are doing is, we are of course iterating over this whole thing, but within one iteration we are trying to minimize this Lagrangian function, okay, on each computer over the local variable x I. So, there is a local variable x I on each computer. So, I am assuming here that I stands, each I is put on one computer, and now we are minimizing this L I of x with respect to the previous Lagrange multiplier iterate, okay, on each computer. So, this can be done in parallel. Okay. So, once we solve this problem in parallel, we can do this update to the Lagrange multiplier. So, in this case the Lagrange number of Lagrange multiplier is exactly n. Okay. So, we can update these Lagrange multipliers by this step, which is the dual ascent step, or which is rather the gradient descent in the dual step. Okay. So, the distributed solution is something like this, that you scatter. So, from a central node. So, if this is your central node and these are your compute nodes, then you send yk to all of these nodes, then you optimize and obtain xi k plus 1 in each of these nodes, which is again sent back to the central node, and then you compute this ai xi and you sum and update and obtain yk plus 1 in central node, and you keep going back and forth. Now, this is a very neat solution, but all the drawbacks of dual ascent exist. So, what are the drawbacks? Drawbacks is basically that if your Lagrangian does not have a unique solution, then this algorithm will oscillate. Okay. Now, here is a solution for that oscillation problem. So, the solution for the oscillation problem is that we add what is called the second order proximal term to the Lagrangian. So, earlier if you remember, the Lagrangian was just this portion. Okay. So, the first portion is the objective function and the second portion is the Lagrange multiplier, which is the penalty for the constraint violation. Okay. Now, we add another penalty for the constraint violation, but this penalty is always positive, and this is like this is a x minus b whole square. Okay. So, this will always, if the constraints are violated, then this will always be positive. So, this will always drive the solution towards the solution where a x is equal to b, which is the original constraint. Okay. So, in other words, we are not changing things at optimality. So, at optimality this is going to be 0 because a x is equal to b, and whatever the solution for this is, that will stay here. Okay. So, minimizing, in other words, if we were to minimize Lagrangian versus if we were to minimize the augmented Lagrangian, the solution will not change. Okay. Now, if this is the case, okay, and we may want to do the dual ascent now. So, method of multipliers is nothing but dual ascent with this augmented Lagrangian. Okay. So, this is dual ascent with augmented Lagrangian. Okay. So, your gradient now changes to something like this, okay, and your x update remains of course same, but your gradient now changes to something like this, or rather the dual update step changes to something like this. Okay. Why this is the case? So, you see, when we are trying to solve this problem, okay, we basically want two conditions to hold. Okay. So, this is coming from let us say something like we have discussed the KKT conditions, Karush-Khan-Tucker conditions for optimality. Okay. So, the first condition that should be satisfied is the primal feasibility. Okay. So, primal feasibility basically means that the constraint should be satisfied, which is that a x is equal to b. The second condition that should be satisfied is called the dual feasibility. Okay. Dual feasibility is basically that you take the gradient with respect to the dual variable, okay, and then you say that that gradient should be 0. So if you take the gradient with you take the gradient with respect to primal variable, that should be 0. So the dual feasibility condition comes when the gradient with respect to dual variable is 0, or so this is like saying gradient with respect to y, L of x comma y, L rho of x comma y is equal to 0, and this is saying gradient with respect to x, L rho of x comma y equal to 0. Okay. Now, if you put this condition here, okay, so you put this condition on this, okay, that so at x k plus 1 your so x k plus 1 is the solution that you get, or rather y k plus 1 is the solution that you get after doing the dual update step. Okay. So, let us say the problem was dual feasible before the update. So, after the update also it should be dual feasible. Okay. So, in other words this should hold. Okay. And you see, if you write, so if you expand L rho of x k plus 1 with respect, so basically you know that the update is so you know that x k plus 1 is nothing but x k plus this rho of a x k minus b. Okay. So, let me just so sorry, this is the update for y variable. Okay. So, you should have the update like, okay. So your update is basically that your y k plus 1 is y k minus rho of a x k minus 1. Okay. So, if you plug in y k from here, okay, so you get so rather if you expand the L rho and then compute the so basically this is your y k plus 1. Okay. So, if you expand the L rho and compute this gradient, this becomes your y k plus 1, and then so you have this A transpose y k plus 1, which is in the same form as your dual feasibility condition here. Okay. So, if you start with the optimality with respect to x, okay, you get the dual feasibility for free. Okay. So, basically that is why instead of, so if you remember there was a step size update here. So, actually this is a special property of method of multipliers, that the step size, if you want to ensure dual feasibility, turns out to be rho. Okay. So, so here rho is the parameter that you have used for this is the rho parameter that you have used for the augmented Lagrangian. Okay. So, basically that is why instead of using an arbitrary step size here, you use like the rho as the step size. Okay. So, this describes the method of multiplier. Okay. So, now we come to ADMM. So, basically ADMM combines both of these. So if we want to step back, okay, so now we want, so method of multipliers has the advantage. So why do we use method of multipliers? Because method of multipliers has the advantage that your augmented Lagrangian, if we were to go back to this augmented Lagrangian, this is always strictly convex. So, this is always strictly convex for any positive rho. So, if you have a positive rho, this is always strictly convex, which implies that it has a unique solution. For x. Okay. So, if you try to minimize the augmented Lagrangian, the solution is always unique. Okay. So, method of multipliers does not suffer from the problem of multiple solutions. Okay. And on the other hand, the dual decomposition method, it actually very nicely splits into multiple optimization problems, which can be solved in a distributed manner on different machines, as we have already shown, and the solution can be gathered and then the update can be made. Okay. So, these are the two properties of two methods, and our objective is to combine the good properties of both these methods. So, combine. So, again for okay. So, so in some sense we should have convergence properties of method of multiplier, okay, and decomposition property of dual decomposition method. Okay. So, both of these should be there, and that is where ADMM comes in. So, ADMM has both these properties. Okay. So, how does it work? Okay. So, so this is the update. So, suppose, so for simplicity here, so we have described two functions. So, your actual thing may be sum over n functions. So, f1 x1 plus till fn xn. Okay. Instead, we are just adding over two functions for simplicity. Okay. And this is the equality constraint. So, for some values of a, you can think that this will be x is equal to z. Okay. So, you can take a is equal to 1, b is equal to -1 and c is equal to 0, and this constraint will be x is equal to z as a special case of that. Okay. So, in general ADMM can solve both these problems. Okay. So, how does it work? Okay. So, as you can see, even in this case the Lagrange multiplier, or rather so the Lagrange multiplier is the same. So, you have the constraint. So, this is the penalty of the, or rather the Lagrangian function is the same. So, you have the penalty. So, this is the penalty term. Okay. This is the objective function and this is the augmentation term. So, this is the augmented penalty function. Okay. Now, the updates go like this. Okay. So, you first update the x variable. Okay. So, you first update the x. So, you randomly initialize. So, initialize randomly zk and yk. Okay. So, you can for the first step you can initialize them randomly. Okay. So, you first solve for x. Okay. Then once you have solved for x, you solve for z. Okay. So, there is an update ordering here. Okay. So, first you solve for x, okay. You get x k plus 1, you plug in x k plus 1 in this Lagrangian now and you solve for z, all the while you keep the y same. And then you do basically gradient descent on Lagrange multipliers, okay, on y, which are the Lagrange multipliers. Okay. So, this is your ADMM algorithm, okay, or algorithm for that is called alternating direction method of multipliers. So, we will see how this can be used. So, we will see why it is not trivial to derive this algorithm. So, you have to actually prove the convergence of this algorithm, and we will also see how this algorithm can be actually used to solve or like a machine learning problem, which is for which we will there is a optimization problem, of course, and this problem can be solved using this ADMM method in a distributed manner in the second part of this talk. Thank you.